This lesson is for Mrs. Cucci's College Now Pre-Calculus class. We are on lesson 4.6, Applications and Models, Growth and Decay, and Compound Interest. We left off on page 1.18, so if you want to go ahead and open that up on your calculator, we can get started. Okay, so the next thing we need to talk about is growth rate and doubling time. So the growth rate, K, and the doubling time, T, are related by K times T equals ln of 2. Or we can rewrite that as two different variations, K equals ln of 2 divided by T, or T equals ln of 2 divided by K, depending on what you want to solve for. So basically, K times T equals ln of 2. Okay, so our first example says population growth. The population of Kenya is now doubling every 28.2 years. What is the exponential growth rate? Okay, so we know that every 28.2 years it's doubling. So what we're going to do is we're going to take our formula and we're going to use one of the variations. The variations that I think we should use is K equals ln of 2 over T. And I chose that variation because what we know is T. Okay, T being the doubling time, how long it takes for the population to double. So ln of 2 divided by 28.2. And then what we can do is we can take that and we can put it right into our calculator. And that will give us an approximate value of 0.0246. And since we want to know what the exponential growth rate is, that's a percentage, we're going to move this decimal two places to the right, and it becomes approximately 2.46%. So the formula is actually pretty simple to use as long as you know what each variable stands for. Okay, so the next example says models of, we're going to be dealing with some models of limited growth. Our formula for limited growth is P of T equals A divided by 1 plus B times e raised to the negative kt. This is called a logistic function, and the function increases towards a limiting value as t approaches infinity. So it's reaching a specified value and it's not getting any larger. So therefore, what we wind up having is a horizontal asymptote at y equals a. Okay, so let's take a look at an example of that. Okay, so a lake is stocked with 400 fish of a new variety. The size of the lake, the availability of food, and the number of other fish restrict the growth of that type of fish in the lake, and it has a limiting value of 2,500 fish. The population gets closer and closer to this limiting value, but never reaches it because of that horizontal asymptote that we talked about a second ago. The population of fish in the lake after time t in months is given by the logistic function P of T equals 2,500 over 1 plus 5.25 raised to the negative 0.32 t. We're going to graph the function, and we're going to find the population after 0, 1, 5, 10, 15, and 20 months. Okay, so what we're going to do is we're going to insert a graph page. And we're going to insert our function. So go ahead and take a second to type that in. Okay, and when we graph it, we don't see the function right away, and that's because of our window. If you think about it, if we know that the limiting value is 2,500, I'm going to have a horizontal asymptote at y equals 2,500. That's very high up on my x-axis, so we do need to adjust my window. So in menu, window settings. My x minimum, since I'm not worried about negative time, I can start that at 0. My x maximum, since we wanted to look up to 20 months, let's go to 25 so it gives us a little bit more room to play. My minimum y value is 0 because we're not going to go any less than 0 fish. And my y maximum, let's say 3,000, because I know that I'm going to have that horizontal asymptote at 2,500, but I want to see a little above it. And here's your function. Okay, so now what we want to do is we want to take a look at the values at 0, 1, 5, 10, 15, and 20. Now the quickest, easiest way for us to do that is to pull up the table and look at the table. So Control T will bring up your table. So we have 0, we have 1,250 fish. Okay. At 1, we have 1,574 fish. At 5, we have 2,335 fish. Remember, you can't have a half a fish, so we're going to go by whole values here. We're going to have 2,487 fish. 15, 2,499 fish. And then lastly, 20, 2,499.94. So notice it's getting closer and closer to that 2,500, but not actually ever reaching it because of that horizontal asymptote. Okay, so let's talk about exponential decay or decay rate in half-life. Our exponential decay formula is P of t equals P sub 0 times e raised to the negative kt, and that negative is what makes this a decay. Decay rate in half-life, we've got that same formula we had before for doubling, so k times t equals ln of 2. Okay, so let's talk about carbon dating. The radioactive element carbon-14 has a half-life of 5,750 years. The percentage of carbon-14 present in the remains of organic matter can be used to determine the age of that organic matter. Archaeologists discovered that the linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon-14 at the time it was found. How old was the linen wrapping? Okay, so since we're dealing with half-life, what we're going to do is we're going to take our formula for half-life, which is k equals ln of 2 over t. We know that our half-life is 5,750. So that's what we're going to put in for t. Okay, we can go ahead and put that right into our calculator. And we get this value here. So what that allows us to do is it allows us to, since we found the rate of decay, it allows us to make our formula. Okay, P of t equals P sub O times e raised to the negative 0.00012 times t. Okay, so this is my first step. I need to find that value in order to build my equation. Okay, this function can be used for any carbon dating problem because that carbon dating has the same half-life no matter what it is. If the linen wrapping lost 22.3% of its carbon-14 from the initial amount, then 77.7, or what's left over, would be the amount present. To find the age of the wrapping, we have to solve that for t, okay? So again, we should have left over, if it lost 22.3, we should have 77.7% left over. And what we're looking for is that value of t, okay? So this is going to go for us. And we're left with, we need to take this and make it into a decimal. Too many zeros in there. Alright. Now we'll take natural log both sides. We know that ln of e is 1. We get this far. Last step. To find that value, we simply put into our calculator. And we get t to be approximately 2,103. Thus, the linen wrapping on the Dead Sea Scrolls was about 2,103 years old. Okay, so step 1 was to find that rate. Okay, once you have the rate, we plug into our formula and then solve out for t. Okay, so the next thing we're going to talk about is curve fitting. We've done quite a bit with curve fitting over the past few years with regressions, so that's what we're going to take a look at now. All right, so spending on video rentals. The number of video stores is declining rapidly. Consumer spending on video rentals from subscription services like Netflix, kiosk, cable, and satellite video on-demand services has increased greatly in the recent years, as shown in the table on the next page. So we're going to see a whole bunch of data. Okay, we're going to use the calculator to fit an exponential function to the graph. We're going to graph the function with scatter plot, and then estimate customer spending on video retail through subscription services in 2004. All right, so first thing we need to do is take a look at our data. And I forgot to put the data in. All right, so we're going to insert the data. So Control I. And we're going to add list and spreadsheet. We're going to label A as our year. We're going to label B as spending. Okay. So for the first year, it's going to be 1. And then, sorry, first year is going to be 0. And then 1, 2, 3, 4, 5, and 6. Okay. The amount spent in the first year is going to, in 2005, 0 is going to be our 2005, is 2.2 million. In 2006 is 2.6 million. 2007 is 3.1. 2008 is 3.8. 2009 is 4.5. 2010 is 5.6, and 2011 is 6.6. Okay, so from here we're going to add in our scatter plot. So Control I, add data and statistics. We need to define our variables, or click to add our variables. Our domain was year, and our range was spending. And like we said before, we want an exponential function. So we're going to go to Menu, Analyze, Regression. We're going to show exponential. Let me get this function right here. Okay. So now what we're going to do is we're going to use that in order to help us determine what the estimation and spending would be for the year 2000 and what did we say we wanted? 2004. Okay. So since we've got our equation there, 2004 is what I'm concerned with, since we know we went by from 2005, which is 0, 2004 is going to be the year before. Okay, so the value that I'm going to need to use, this is supposed to be 2014. That would make much more sense than what I was confusing myself. 2014. Okay, so 2014, if I know the 6 correlated to 2011, 2012 would be 7, 2013 would be 8, 2014 would be 9. So the x value of 9, if I were to put 9 in for my x value, is going to give me the estimated spending. So what I'm going to do is I'm going to bring up a calculator page, and I'm going to store x as 9. Okay, and I'm going to use my equation to determine the amount of spending. So 2.16966789506. 2.16967, I guess we can stop at. Times 1.20421 raised to the x. So it's about approximately 11.6 billion. Dollars. Spent in 2014. Okay. Last thing is just a formula that I'd like you guys to know. Converting from base B to base E. If I have B to the x, in order to convert that to base E, we're going to do E to the x times ln of B. So that's just a quick conversion, and we'll talk about that more later. All right, thanks guys.